Today's topic is absolute value functions. We're going to put the fun into functions today. The function f of x equals the absolute value of x is very similar to the line y equals x. Why is it similar? Because if you take a look at what the line y equals x looks like, it's a nice line that goes like this. But as we've studied absolute value, we know that the absolute value of anything negative turns into a positive. So, to visualize the graph of the absolute value of x, we have to modify the graph up here of f of x equals x or y equals x. For any value, when x is positive, the graph is the same because it's already positive. But when x is less than 0, the graph is less than 0. That's very bad because when we're taking the absolute value, you can't have a negative number. So what we do is we have to fix this. And we do it by folding, which isn't the mathematical term. The mathematical term would be reflecting. We reflect the chunk of the graph right here. That's negative. We reflect it over the x-axis. So it's going to be something like this. Now it's going to look like a big V. And the absolute value of x, the base graph of it looks like this. It is a V. Okay? That's what the absolute value of x looks like. This is another mother function. You need to make sure you remember all of your mother functions. The other mother functions we've looked at is y equals x squared, the quadratic function. We know that one. Now we also know the absolute value of x. All right. Now, here's where it gets a little trippy. Okay? Now, we are going to use a brand new type of function that you've never seen before. And this is called a piecewise function. Now, before I tell you all about it and how it relates to the absolute value, let me give you an example of what a piecewise function might look like. Let's say you have a nice x and y axis that looks like this. Now, think of it like this. Let me say if I said to Drayden, come and draw a function that you like. And let's say Drayden drew something like this. He drew, and then he stopped. Okay? And then let's say I invited Jenna up, and from that very point, she drew a horizontal line. The red and the blue are two different functions. Two different functions. But think of this as taking two functions and joining them together and making one function. The difference is, or the key point is, not the difference. The red function is only defined up to a certain point. When Drayden stops moving his pencil, the function is no longer defined. It would be defined from negative infinity up to whatever this x value is. And then Jenna's function starts at that x value and would go all the way to positive infinity. This is a piecewise defined function. You can have a piecewise defined function that has two pieces like this. You could even have a piecewise defined function that has 3 pieces, 4 pieces, 5 pieces, okay? But this is what a piecewise defined function is. All it means is it's going to be one function for a little bit of time and then another function for another bit of time. That's it. It's not harder than that. Now, with the absolute value function, here's how it's defined. The absolute value of x is the same as saying the graph is just plain old x if x is greater than or equal to 0. But if x is less than 0, it's not x anymore. Because if it was x, it would go below the x-axis. So to reflect it up, we have to put a negative sign in front of it. So it's negative x. Okay? All right. Now what we're going to do is we are going to take a look specifically at this function right here. Y equals the absolute value of x plus 1 minus 2. Okay? Now, what does this look like that we've already studied? So we could think of this as similar to vertex form. Cool. And if we did that, what's the vertex, or not a vertex, but we're going to think of it as a vertex. What's the vertex of this thing? -1 and -2. So we find -1 and -2. We don't have a scale here, so let's make a scale. -1, 2, -1, -2 rather, would be right here where I've drawn this nice, beautiful black circle. And now, understanding that this is the line y equals x, basically from this point, it's going to go over 1, up 1, over 1, up 1, over 1, up 1. So you got to grab a ruler, draw yourself a nice, you don't have to have a ruler, just something that draws a straight line is fine. I can't really draw a straight line so easily on this silly thing.
No, plus b cubed.
Well, that's true. I'm just going to draw a freehand.
This one would be
Uh-oh. No, that's good. There we go. That's the first part. What's that? No, there isn't. And the other one's going to look like this. Like this. So that's what it looks like. That's what this function looks like. All right. What are the intercepts? So if we just talk about the x-intercepts, what are they? -3 and +1. What's the y-intercept? -1. So those are your intercepts. What's the domain and range?
domain is negative infinity to infinity.
Good. Domain, negative infinity to infinity. That's right. And the range is square bracket, -2 to infinity. Because it does equal -2. So because it does equal -2, we can use the square bracket.
This one would be 10. Transformation.
Now this question, I'll be honest with you, I intended for us to do this a whole different way. I intended for us to use a table of values here, which means plug in an x value and figure out a y value. So we're not going to go through that, but I'll just show you what you would do. You would make a table, and I would probably, if I was making a table of values, I would go from -3, and I'd probably go up to 3. And I would plug each of those values in to the original equation, and I would write their corresponding y values. And if you did something like that, and then graphed your ordered pairs and connected the dots, that would be great.
Would it come up the same?
Absolutely. Absolutely it would. As long as when you calculate those values, you do so correctly.
No, 5B.
So I really like Drayton's relationship between this and the vertex of a quadratic. Because if you see it that way, it allows us to use our rules for quadratics in order to graph this. At least the idea of where the vertex is. Because if you know that, then it's all good, man. And if you forget that, you can fall back on the idea of using the table of values. Now, the second part, I say use transformations. Well, we kind of did use transformations here. Because if it was just the absolute value of x, by having the +1 inside the bracket, we moved the middle left 1. And because we saw the -2 on the outside, we moved it down 2. So you could think of it that way when you're doing these graphing questions.
And we still flip the one in the brackets, right?
Yes, absolutely. Last question. Here we go. And we definitely saved the best for last. We have the absolute value of x squared minus 9. Now, we've seen x squared minus 9 before. That's a quadratic. So we're going to start off by graphing this as a quadratic. So let's figure out a scale here. I'm going to say a decent scale for this would be 1, 2, 3, 4, 5, -1, -2, -3, -4, -5. And for the y's, we'll just go to 10 and -10.
8, 3 would be 5, that'd be 10, and that'd be 8. Or it would be 6.
Well, what's our vertex?
8x. It'd be 6x.
The vertex of this is 0, -9. So it's just going to be right here. That's where the vertex would live.
Wait, where'd you get the 0?
Because there's nothing inside the bracket, right? It's x plus 0 inside the bracket. So there's no number inside the bracket, so the number's a 0. Well, because this is the same thing here as, right? If it's a 0, it's just x squared by itself. Okay? If it's a 0, it's just x squared by itself. So this is a bit of a slippery one. Okay? Now, from this point, we go over 1, up 1, over 1, up 3, over 1, up 5. So let's do that. What's that? Why what? Because that's how we learn to graph quadratics. 2 units ago. 3 units ago, actually. No. Yeah, 3 units ago. So over 1, we have to go over 1, though. up 1. So it's over 2, because every 2 units on this graph is 1, so it's over 2,
plus
up 1,
9x, y,
over 2, up 3,
3,
and then over 2, up 5.
10. Yeah. 10.
And then
10x, 3,
over 2, up 5.
that would be 5. Over 2 up 5.
Sorry, not 5, sorry, 7. 7, my bad, it's 7 now.
X squared.
So that's 7 here,
3.
and 7 here. So this is nothing to do with absolute value yet. This is all to do with quadratics, graphing quadratic functions.
20 more questions.
So that is what y equals x squared minus 9 looks like. So here we go. The problem with this graph is this part right here is under the x-axis. Any point that's below the x-axis is negative. So what we have to do is we have to fold it over the x-axis. Because the, if you look here, the lowest the graph is ever vertically is on the x-axis. Y is equal to 0 on the x-axis, which explains why the low value for the range is 0 and the high value goes to infinity. How do we write this as a piecewise defined function? I have left the best to last. Now, so this is going to have to, this should be looked at as 3 distinct parts, and 2 of them will be the same. But the graph acts normally on this first part and on this last part. And we had to reflect it in the middle. So we are going to make this as 3 parts. So we're going to say, and copy this down and pay attention to the way we write it, f of x equals, and the first part, I'm not writing in what they are yet, I'm just going to write in where they are. The first part is when x is less than or equal to 3. That's this first part of the graph right here. The last part is x is greater than or equal to 3. And that's this part right here that's also red. These are the normal parts. The not so normal part is between 3 and negative 3, which reminds me I made a boo-boo here. That should be negative 3, my apologies. So we've got x is less than negative 3, x is greater than positive 3, and we also have x is between negative 3 and 3. Now, I've already said this, but I just want to kind of do a check-in to see if you're absorbing this and paying attention. These are basically 3 parts of the graph. Which parts are the graph behaving normally?
Less than or equal to negative 3.
Yeah.
Greater than or equal to.
Then the rest, right. So in both of those spots, it's just going to be x squared minus 9, x squared minus 9. Nothing changes for those. Nothing changes for those. It's just x squared minus 9 in both of those regions where the graph behaves normally. The only place where we had to fold things and the graph doesn't behave normally is between those values. And think of it this way. Let's go back to quadratics, shall we? What we did is we folded or reflected things over the x-axis. What did we have to do to a quadratic function to fold it over the x-axis? What did we have to include or add?
Y
Plus 2.
squared.
And you don't have
X.
plus 6.
Subtract 9.
A negative sign. So all we're going to do is we're going to write x squared minus 9 in brackets with a negative sign in front of it. And that is all it takes to flip that bad boy upside down and reflect it in the x-axis and make sure that any of those values that were negative now become positive.